like to welcome all viewers to this webinar today hosted by the IIT Alumni Center, Bengaluru. Before we begin, the IIT Alumni Center, Bengaluru is kind of a unique alumni institution that has been set up in Bangalore, in the city of Bangalore. We have our own facility coming up within the next few weeks now, just near the Electronic City area of Bangalore, 100,000 square foot facility where all the 23 IITs will have offices. And we have an incubator and so on and so forth. It's a fairly nice and iconic building for the city. And hopefully it will be a science and tech hub for the city in the years to come. Today's webinar is the 70th that IIT Alumni Center Bengaluru has been anchoring since the start of the pandemic. And, you know, we believe we've had a collective viewership of over 35,000 people who have either seen it live or watched the YouTube replays. Typically, the YouTube replay is available from the following Monday on the IITACB website. Quantum computing, I think it was in 1994 that Shor's algorithm became well known. You know, Peter Shor, the mathematician, came up with an interesting way to use quantum techniques to solve factorization of large numbers. And that kind of scared the cybersecurity industry in a big way because it could crack things very, very quickly. And an entire new area of using quantum tech in security applications came up. Similarly, I think in 2019, if I'm not wrong, Google's Sycamore came up with their own, you know, bragging of saying that we managed to do in 200 seconds what classical computers would take thousands of years to do or whatever. So just looking at just these two areas, you know, the security applications and, you know, high performance computing, there are many, many, many ways where quantum computing will make a big difference as we go forward. India has made an investment also, I think it was 2 or 3 years ago when the Honorable Finance Minister made a commitment of investing, I believe it was 8,500 crores in a national quantum mission. And we are fortunate today that we have Professor Anil Prabhakar, who is deeply involved with the National Quantum Mission. Anil is a professor at IIT Madras. And he's also kind of a serial entrepreneur, if I may, sir. Two startups called Q New Labs and Quanfluence. They are India's first startups in quantum communication and photonic quantum computing. Welcome, Professor Prabhakar. Professor Alok Shukla from the Department of Physics at IIT Bombay. And, you know, before joining IIT Bombay, he was a visiting scientist at the Max Planck Institute in Germany, where he spent several years. And he has done some interesting work, and he will be moderating the conversation today with Professor Anil Prabhakar. Some housekeeping for our viewers. Please put your questions in the Q&A box only and not in the chat box. The moderators will be looking at the Q&A box and not at the chat box. Chat boxes are usually, in our scheme of things, we serve it to kind of for just internal communications, or if somebody wants to send a message to one of the panelists, that's good for, but not a question. So Q&A has to be used for questions. With that, Anil, I hand over to you to take this forward.
Thank you, Ashok, and it's a pleasure to talk to the audience here who are attending this talk. As you did mention, the National Quantum Mission has been on the anvil for the last 3 years, and we are hoping that sooner than later we will actually operationalize it. But in the meantime, there is enough happening that we should all be excited, and I'm hoping to share some of that excitement with you today. Okay, so I titled this talk as Translating Quantum Technology for a particular reason that a lot of quantum technology is often hidden under various shrouds of secrecy behind black curtains in labs or at very cold temperatures. And one of my aims has been to see how we can actually commercialize some of these ideas and provide societal benefit. So to that extent, I thought the title would be more apt to focus on the translation aspects. And I will give you a little bit of background on what the technology buzz is about. What is the National Quantum Mission that we're talking about? Then we'll get into some details. I won't, I'm a little nervous about giving too many details because it could become very technical, but you need some details to understand the terminology that is being used. And then, of course, the takeaway message is, how do you translate this quantum science into technology? And when will we see quantum technology working at scale? So when I mean at scale, it means that it's ubiquitous. It's everywhere around us. We don't necessarily need to go into, come to my lab or a colleague's lab and look at science experiments. So let's hopefully get there. Very briefly, I'll reiterate my background. I did a PhD in applied physics in '97. And my first job was at a company called Quantum, which was unusual because at that time, quantum was still not the buzzword. Quantum technology today could be both microwaves or photonics, and we'll be talking about both of them today. And if you look at my serial entrepreneurship, as Ashok mentioned, we have worked at QNU Labs with quantum communications and now Confluence for photonic quantum computing. So hopefully they will both be companies that will run the course and you will see them succeed in the near future. Our own quantum technology, when I say our, it's me and my colleagues here at IIT Madras. We are at the Center for Quantum Information, Communication and Computing, or CQUIC. And we have 3 different areas that we work on. One is building quantum networks. One is doing quantum computing itself. And the third one is building our own hardware. My first experiments on quantum networks or quantum communication was as early as 2010. But at that time, people were not quite interested in it. However, by 2016, people were interested again, and you have to ask, why was there a sudden increase in interest? Because after all, as Ashok mentioned, an algorithm by Peter Shor was discovered in 1994. So why was there this huge gap of almost 20 years before people began taking the quantum technology seriously? In fact, in 2010, when we first demonstrated quantum key distribution or QKD, there wasn't as much interest in our demonstrations. But by 2016, people were asking me to do it again, and I had learned my lessons, and I decided to incubate a company to do it. In 2022, IIT Madras joined the IBM Quantum Network. We are now an IBM Quantum Innovation Center, and that gives us access to the latest hardware from IBM on their technology platform, and I will explain that in a bit. And finally, as we began exploring our own ways of building hardware, we also incubated Confluence sometime last year. Right? The number of people who work in this area, as you can see, I've mentioned the departments. It's not just physics, it's not just electrical engineering and computer science. There could be from all kinds of departments. And you should get that sense as you listen to me talk, because you will see that the problems that we're trying to solve require a very interdisciplinary approach. This particular slide is actually borrowed from IBM. It's IBM's roadmap on quantum computing. And you will notice some of the details, you cannot see them. The resolution is not very good, but you'll obviously can see that there is an inflection that's happening at 2022. And that coincidentally was also when we began actively engaging with IBM on their quantum computing roadmap. Ashok mentioned a particular instance where Google claimed that they have achieved what would in local parlance be called quantum supremacy with a much smaller machine. And you can see out here that IBM is actually already released 400 qubits and is promising to release 1,000 qubits this year. But to understand the importance of that, we also need to understand why we are interested in qubits and what value we can create. Some of the applications that are listed out here include quantum chemistry, optimization, cryptography, and also basic science. So you can solve certain problems like many-body physics and quantum tomography, which involve quantum mechanics at a very fundamental scale. So if you want to simulate those, you have to actually do them on a quantum computer. And of course, this is not something that only academia can do. There has to be industry and startups involved in this. And that is some of the work that we do at our center. The faculty itself, as you can see, are interdisciplinary, and even our support is a fairly broad spread. We get support from Emphasis, DST, many ministries. We have L&T Mindtree, we have Nagaro, we have Bharat Electronics. So the list of supporting cast is quite large. And that's because if you start looking at the kind of range of activities that one must undertake when we start looking at quantum technologies, you will realize that they span the entire gamut of information theory, simulations, applications, devices, systems. So this is a snapshot of people who are involved. Just the faculty, if you assign 3-4 students and staff to each faculty, you will understand that it's a very large endeavor. Okay. So coming back to the main topic, what is this quantum computing race about? And I promised that I would tell you a little bit about the different technologies. And so this slide, although it's busy, is a little color-coded. It's by no means complete, because every day I hear of new companies that are joining the race. But the main ones you have are IBM, Google, D-Wave, which is Canadian, and Rigetti, which is a startup in California. You have Intel, Alibaba, IQM from Finland, and Amazon. And these are all coded in green. We have our own Indian startup, QPi AI, and they're working with IQM and trying to build this technology called superconducting qubits. And that is one of the technologies that I will spend some time on today. You have Quantinuum, which was spun out of Honeywell, and IonQ that provide ion traps. And you have Xanadu, PsiQuantum, and Quanfluence that are working with photons. And you have Microsoft that is pursuing topological insulators. In fact, I think only last month there was or maybe earlier this month, there was an announcement from Microsoft claiming that they have managed to work with topological insulators. And Intel does what it does best, which is it works with silicon. And so it is working on a technology called spin qubits and is expected to release that this year. Why am I telling you that there are so many technologies is because the applications change with the technology and the way it has been implemented. It's the very early days of, let us say, microprocessors, where everybody had their own way of doing things and there was no standard. And so you could actually get trapped into pursuing a particular platform and find that maybe you're not bet on the winning horse. So to that extent, it is wise to always keep your eye out on all the different technologies that are available. At the bottom right in purple, I have mentioned circuits versus annealers, and that is also an interesting differentiator. We tend to think of computers in terms of logical bits, but there are people who do what is called analog computing. And annealers would be closer to analog computing than digital computing. And digital computing would be what we are now currently looking at on our desktops and our laptops. So there are different ways of doing computing also. And D-Wave, which is a Canadian company, specializes in building annealers, which have their own advantages over circuit-based systems that are built by the other players on this slide. So if you look at why we are looking at all these things, it's because they all offer different advantages. And there's Professor David DiVincenzo, who works at RWTH Aachen in Germany, and he came up with this criteria saying that you need to understand to be able to compare different technologies. So there are certain metrics that we use. As an example, the lifetime of a qubit, which is written in the second row as 50 microseconds to 50 seconds, it determines how long the qubits can store and process information. Now, remember, on a classical computer, we don't really worry about this. In fact, I think we should probably have a self-destruct mechanism, because there will be umpteen copies of everything that we have saved and backed up, and it never dies. However, on a quantum computer, you have anywhere from 50 microseconds to 50 seconds to finish your computation, after which you lost your ability to do that, because as of today, we still don't have a quantum memory. So to compare the different technologies that are listed on the left from 1 to 5, you must compare them correctly. You cannot compare apples to oranges, and sometimes the comparison is not even possible. IBM went ahead and defined a metric called a quantum volume that is specific to superconducting qubits. And it's ironic that if IonQ, which was a startup, were to use IBM's metric of quantum volume, they would beat IBM by factors of 1,000. That's because their technology was very different, and it has its own set of problems. And it's really not the right metric to compare it with the superconducting qubits that IBM uses. So with those caveats, I'm going to jump in and show you some photographs, and you'll understand again why I was warning you. So the Google chip, which was called the bristle cone on the left, it had 72 qubits. They may have increased it. IBM has released 400 qubits. Rigetti is at 80 qubits. And D-Wave has blown them out of the water. He says, I've got 5,000 qubits. What are you guys talking about? Well, D-Wave is not building the kind of computers that Google, IBM, and Rigetti are doing. They're using the same technology, but they're building an annealer, right? So it's unfair to do that comparison. Similarly, Quantinuum or Honeywell has 150 qubits, and they are on ion traps. And they do very differently. And there are other companies that are following other technologies. So with that in mind, I just want you to, sort of give you pause to say, don't believe that number is the only metric out here. It is not like classical memory, where if you pay more money, you get more DRAM. The quality of the memory, or the quality of the qubit in this case, matters a lot, and not all qubits are equal. Yeah, so what you actually see out here is not is the entire stack. It's like if you would look at a desktop or a high performance computing engine, right? You'd see an entire rack full of servers and everything. And that's what you're seeing out here. Although right at the bottom is this little chip that is placed out there, and it operates at some millikelvin temperature. 0 Kelvin is absolute zero, where everything freezes and you cannot do anything at all. And we are 20 millikelvin above that. And you have to ask, why do we have to operate it at such a low temperature? It's because quantum systems are very sensitive to the environment, and we are trying to eliminate all the noise that is possible. And the main source of noise is thermal noise. In fact, temperature is a measure of thermal noise. And by cooling it to these ultra low temperatures, we are able to get to the point where we can actually observe quantum effects in these computers. An alternative to this is a Chinese machine which uses photonics. And if you look at the photograph on the right, that photograph is a example of the architecture that they built on the left. And it's a complicated stack of optical elements all aligned up so that the light passes correctly through this array of crosses. And they claimed supremacy, and they claimed a much larger number than what Google did or IBM attempts to do. Google's claim, incidentally, was very quickly rebuffed by saying that when somebody was able to solve the same problem with random circuits much faster on a classical computer, it did not take thousands of years. I think it was done within a couple of years. And that is also a danger in this game, that you think you may have done something, but your competition, which is the classical computing, is not sitting idle. And they are always reinventing themselves to do better and better. So it is a race that is going on. But photonics also provides a path to a scalable quantum computer, and it works at near room temperature. I say near room temperature because we still would want to keep it cool, but maybe not millikelvin. We might do, hundreds of Kelvin, like liquid nitrogen temperatures or liquid helium temperatures. So in order to grapple with this idea, we ourselves came up with what is called a grand challenge of 25 by 25, where we said, and we ran it in the past few months, it just got over last month, where we said, look, everybody's claiming different things. Why don't we look at particular problems and see if we can solve them on the quantum computer? So what are the typical problems? Protein folding. That's an interesting problem. It turns out that protein folding, which I first heard when I was a graduate student, is still not a solved problem. And of course, we are solving very simple protein structures, not the really complicated ones that make life tick. There is factorization, which is what Ashok had mentioned. If you take a large number and you want to factor it, so we can do, let us say 21 very easily. 21 is 7 times 3. I could probably do 65 as 13 times 5, and so on. But after a while, even our computers cannot do it. And factorization is a problem that can be solved thanks to Shor's 1994 algorithm on a quantum computer. There's quantum chemistry, which is a very useful. For example, lithium hydride batteries. Can you improve their performance? Then, of course, there's a favorite one that every student picks up, which is stock price prediction, because we all want to be very rich. Unfortunately, the minute somebody cracks that algorithm, everybody knows it, and so nobody makes any money. There are more useful applications, for example, as anti-money laundering and fraud detection. We were able to do some kind of work on the Ethereum blockchain to identify phishing networks. So there were all these kind of applications that were part of our grand challenge. Right? And that was just a flavor to give you a flavor of what type of problems one would tackle once you have a quantum computer or access to a quantum computer. So the larger picture, what I call the grander challenges in quantum science and technology under the National Quantum Mission. There is one that's coming up next year by IBM called the 100 by 100 challenge on quantum computing. And that you will use cloud hardware, and it may even use photonics, because now all these computers are available to us on the cloud. IBM runs its own cloud architecture. Amazon has its own cloud architecture that allows you to use different computers, while Amazon is trying to build its own. Microsoft Azure Q has its own quantum computing architecture. On the quantum communication side, there are other challenges. We are fairly advanced in understanding of quantum communications. But in terms of reducing the size, weight, cost, we still have ways to go on that. And so there is work to be done on systems and networks, and as well as on materials and devices. I'm just mentioning out here one of the centers at IIT Madras called QCNDM that actually works on materials and devices, and I have a few slides that I will show you. These are only two of the verticals of the National Quantum Mission. There is another one that focuses entirely on sensing and metrology, because quantum sensors are also something that are gaining traction. And there is a possibility of having a vertical on quantum materials and devices, which actually cuts across all these other verticals of computing, communications, and sensing. I always encourage people to collaborate and compete, because this area is so broad. You have to imagine that the days where people were just putting together the first transistors into computing machines, and you'll understand that there's just so much work to be done that it cannot be done by individual groups in any single institution or even in groups of institutions. If you come back to IIT Madras itself, we have a certain platforms that we specialize in. We specialize in our photonics platforms, and we also work with whatever qubits we can get on the cloud to do quantum algorithms, machine learning, information science, right? It's interesting that we do diamond photonics, and that is something that is actually gaining a lot of traction in the quantum technology space. It also, you may have heard the announcement recently where the Prime Minister gifted the First Lady of America with a lab-grown diamond. And those lab-grown diamonds, if you can grow them not at what is called commercial grade, but for electronic grade, then they become useful for quantum technologies. So that is one of the areas that one does look at very aggressively to see is, can we use lab-grown diamonds to build quantum repeaters, right? So what are the kinds of materials that we look at? So if you look at quantum diamonds, and this is a slight digression because this is the sensing approach, you can build magnetometers. So we are all familiar with these MRI machines, and there's a large superconducting or a squid out there, superconducting interferometric device. And those can be replaced by these small diamonds that are then they're used to functionalize water and then sent into your body, and you can do your measurements without getting into an MRI machine. And that would be very interesting, right? They're also good as detectors. They can measure magnetic fields at very low scale. The numbers usually quoted are femtotesla. And just to put it in perspective, femtotesla is maybe a million times smaller than what you would do with the accelerometers or the magnetometers on a regular chip that you may find in one of your phones, right? So these are sort of the applications from a material standpoint, and these feed into some of our other applications at the system level. This is an example of a quantum enhanced sensor where you put this diamond on the tip of a scanning electron microscope. And then if you have a magnetic sample surface and you scan the tip across it, you will pick up the magnetic fields. This is actually something that without this nano diamond at the tip, we were doing regularly to understand recording devices. Now we are able to do it more sensitively once we have these nano diamonds sitting at the tip of our scanning electron microscope. Here are some pictures that show you what the photonic structures would look like. These are what we would call meta surfaces, and Hollywood is always ahead of us. In fact, I dream of teaching these courses called electromagnetics in Hollywood, because the invisibility cloak is a meta surface. It's just that when Hollywood does it, it is invisible at all wavelengths, whereas when we build it, it is invisible at one wavelength. So you can just shine a different colored light and it's visible. So we have a ways to go to catch up with Hollywood. But I think these are interesting avenues. And what you'll see at the bottom left out here is that you have a quartz substrate and you have grown diamond on it and you have etched this meta surface in there. Right. Similarly, on the right, you can see little pillars that are grown and you could have each of them as a quantum emitter, right? So these are sort of the materials research that goes on that eventually have to be translated out into functional systems that we can then use for our other applications. Okay, so that is sort of the background on what the quantum technology buzz was about. I'll give you some details now on how we are building some of these things. And as I promised you, I will talk to you a little bit about the gate circuit model and the annealers. Right? Okay. So the details. I like this particular picture because it tells you how to think about it. And it's titled as waves interfere. So you think of throwing stones in a pond, which is the pictures that are shown on the right. And you'll see that the ripples that are formed when you throw two stones, they will have highs and lows, or nodes and antinodes. And those nodes and antinodes are due to the interference of waves. Similarly, if you throw many of these stones, you would get many more interfering patterns. And depending on what we call the phase of the wave, we get a different computational result out. The numbers on the left show you that if each of these stones was actually a qubit being the quantum bit, which is the analogy we use from the classical bit. So if you have a qubit, and with each qubit, if I go from n equal to 1, 2, 4, 8, I'm actually increasing the number of computational parts as 2 to the power n. By the time you hit 64 qubits, you have reached a computation path that far exceeds anything that you can do on a classical computer. Now, wait a minute. If you've actually been paying attention, you will know that I had said that Google had 72 qubits, IBM had 400. And of course, D-Wave had 5,000 and IonQ had 150. But let's not go there. Right? Let's just focus on, let us say IBM, it says it has 400. That means that today, I should be able to do immense number of things on a computer. But I will caution you, I had also mentioned that the metrics by which you measure these quantum computers has to be kept in mind. Because when we say we have 64 qubits, we mean that we have them error-free. Whereas the quantum computers that we have available to us today have lots of errors on them. So 64 might actually be the equivalent of 6 or 3 if they are not error corrected. And when you try to put in error corrections, you lose factors of 50 or 100. So you may not actually be at 64 qubits, you may be at 2 qubits or 3 qubits, in which case you could actually solve it on a classical computer much faster. The other message out here is that in quantum mechanics, particles can act as waves. And you may have heard that already from your high school science. There is another version of quantum mechanics, which is called second quantization, where we say that waves like optics and photonics can act as particles, right? So the first quantization told us that particles like electrons would act like waves, and the second quantization told us that what we traditionally considered as waves, which was light, could act as particles. And this is another classic experiment that you may have seen, which is to say that, look, if I take a particle and I shine it on a double slit, then I will get behind the double slit only 2 lines, which would be the case if it was entirely classical. So if I have tennis balls being thrown at 2 windows in a wall, the tennis balls will accumulate only behind the windows. On the other hand, if I have quantum particles, then they go through the slits in a manner that acts like waves, which means that you will see those little circles drawn on the right, and those are your ripples that are moving forward. And everywhere those ripples intersect, you get constructive interference and you get accumulation of particles. And that means that I no longer have 2 stripes, I have many stripes, right? And this is fundamentally the idea that we try to exploit when we start using quantum computers, that the particle is in what we call a superposition of the two slits. The left slit and the right slit could be 0 and 1 for us, and the particle is in a superposition of both those states of 0 and 1. And consequently, the output could be anything, could be a wide range of results, not necessarily what we had at the input. So keep that thought in mind and look at this particular slide, which says the magic of superposition. So what it means is that if I started off 0 and 1 for the bit x, and I have some function that is being evaluated, my output is actually that evaluated function for both the inputs 0 and 1, right? So I start with not just a bit which is 0 or a bit which is 1, but I start with a superposition state, which is a combination in this particular case of equal probabilities of 0 and 1. And what I get at the output is the function evaluated for both those cases of 0 and 1, which makes no sense at all unless you try to make a measurement. When you make a measurement, I will get f of 0 if I make a measurement for the 0 bit. If I make a measurement for the 1 bit, I will get f of 1. But that's very, very, very powerful, because now if you think of it, if I had n qubits, I could evaluate 2 to the power n times in one shot, right? Well, it turns out that these quantum computers are noisy, and one shot is not enough. I may have to evaluate it many times, but it's still less than 2 to the power n. So even if I evaluated, let's say n is, I don't know, 64, 2 to the power n was 10 to the power 19, I don't have to really evaluate it 10 to the power 19 times. I just have to evaluate it maybe 10,000 times, which is 10 to the power 5. So I have a saving of 10 to the power 14 out there. And that's pretty much the magic of superposition that we are relying on. So this is a fairly unique hardware, and we use it to solve hard problems. And I've again broken it up into circuit-based systems and annealers. The circuit-based systems are traditional gate-based. You use qubits as inputs and you take a measurement as an output, and it relies on the properties of entanglement and superposition. I have not really explained entanglement, but superposition I've explained, right? The annealers, on the other hand, are more like wave-based computing, and they rely on superposition, and they do what is known as energy minimization. So the annealers, my sort of analogy when I talk to students is, imagine that you're filling a box with rocks and pebbles, and you want to get the minimum energy. You just keep shaking the box. All the pebbles will go to the bottom of the box and the rocks will stick out of the top. And that would be a minimum energy conservation configuration. So the annealers try to do something like that, whereas the circuit-based systems are trying to look at each of them and saying, is this a rock or a pebble? And then taking a decision and putting it back into the box. If it's a pebble, put it first. If it's a rock, keep it aside, and trying to do a sort while trying to do that. So it is obviously a slower process. However, each of them has their own advantages, and depending on the problem you're trying to solve, you do either of them. In fact, we don't even do that. We now rely on a hybrid computing, which does classical and quantum mechanics. So in this particular slide, which is a little busy, what we try to do is we show that we can take learning algorithms that are executed on a classical device with classical data. You can do a classical device with quantum data. You can do a quantum device with classical data, and a quantum device with quantum data. There are all these different ways of doing computation. And in many cases, we are actually adjusting some parameters. And today with machine learning, we are using the machine learning to adjust the parameters of our quantum computer. And that is allowing us to do better than if we were to just try to figure out what the parameters of a quantum computer should be. There are many quantum algorithms. So it's not even fair to say that if I have that DiVincenzo criteria and I'm able to compare two things, that they will work the same. No. Depending on the algorithm you use, you may get one particular hardware working better than another hardware. You'll see out here at the bottom some of the implementations. So for example, the problem solved on Shor's algorithm is factorization of 21. Excuse me, I could do that in my mind. There's nothing great out there. But imagine if you had to factorize something that had, I don't know, 128 bits. That would be difficult. There are algorithms that will do linear algebra. That HHL algorithm does linear algebra. So there are many such algorithms that are used, and each of that is again a research area. The ones that are important, interesting in the above table is the complexity class of each of these, right? So you have polynomial time algorithms, you have more than polynomial time, you have polynomial time on a quantum computer, and so on. So one has to actually pay attention to all these details when you start reading these newspaper articles that claim quantum supremacy and so on. What was the problem that was solved? What was the hardware that was used? Is it truly an example of doing something on a quantum computer better than what was done on a classical computer? Here is a simple example that I use because it's easy to understand, that a classical random walk takes exponentially more time to find an exit than a quantum walk, right? So if I have two nodes from A to B, and as the complexity of that graph increases, if I want to find the paths from A to B, the shortest path, it's harder to do it on a classical computer than on a quantum computer, right? Similarly, AND or tree graphs on a classical computer versus a quantum computer, the quantum computer does a slightly faster job. So the algorithm development is something that is also ongoing right now to understand what are the best use cases for a quantum computer. This is the one that I mentioned earlier. You can do linear equations. We have all done 3x3 matrix inversion, and we know how to do it on a classical computer. You can also do it on a quantum computer faster than on a classical computer. Now, if the matrix is small, then it doesn't really matter and you don't want to use a quantum computer. But if the matrix is very large and it's sparse, then you have some benefits if you do it on a quantum computer. So when do we use a quantum computer and when do we use a classical computer? And there are two main algorithms that people look at. One is called Grover's search, which is searching for a large database, which is why a company like Google would be interested. And then the Shor's factoring. And what this graph is trying to emphasize is to say that don't use a quantum computer for everything. Understand the problem. If the size of the problem is small, then you're better off using a classical search algorithm. If the size of your problem gets larger than the crossover point, then you will start seeing some advantage of using a quantum computer. Even then, there will be a lot of classical pre and post-processing steps that will allow you to use a quantum computer to some advantage. Okay, I hope I've given you some of the details that are required. This is a chart that we look at to say, what does our quantum future look like? And, we are now in 2023. You'll see that this window of opportunity that is there, I seem to have missed out. Oh yeah, it says there's adapted from Gartner from 2018. It says there's a window of opportunity for certain types of problems like optimization, combinatorial logistics, and quantum machine learning. In another 10 years, we will be looking at much larger business cases. But by 2035, there is a serious risk that we will be breaking encryption. So we're talking of about 10 years from now, we will lose all our encryption. Now this, sometimes keeps people complacent. They say it's 10 years away, I don't really need to worry about it, but it depends on how long you want to keep your data secret. So for example, if you're looking at your Aadhaar data or your personal healthcare data, medical information, or maybe their strategic secrets that you wish to retain. Today, they may not be at risk, but someone could steal that data and keep it for 10 years, and then they can decrypt it. And that means that we have the risk today from what is called the save now and crack later scheme, right? So someone could save your data today and have access to it as soon as they have access to quantum computers on the cloud. Before we do that, there are other lower hanging fruits in finance, optimization, logistics, data mining, drug design that we will get to over the next 3 to 5 years. So we are fairly optimistic that this is going to happen. And the question is whether we are going to be early adopters or whether we are going to come in later after the algorithms and the hardware has all been built out. On the y-axis, you'll see what we are aiming for. By the time you hit about 10,000 logical qubits, this is where all the risk starts happening. So as I mentioned, we are at 433 today, and we are expecting 1,000 by the end of this year. The 1,000 chip is of a new kind, which allows parallelization, which means that you could have 10,000 in another three years. And that could become a real risk for a lot of businesses. This is another slide that talks about who will create value from McKinsey. And it's broken up into medium term and long term. Medium term is within the next 2-3 years, and long term is again 10 years. And you'll see that there are finance companies, energy companies, public sector, healthcare. They're all at different levels of value chains, and you could imagine that a lot of the applications will start coming out. And it's reports like this that encourage startups in the space. And you'll see that the startup valuation in 2021 itself went close to $2 billion, right? So there's a lot of investment that is happening, both public and private, that encourages people to look at the startup space. Okay. So some details now on the gate circuit model versus annealing, and then I will pause. Maybe I will just do a introduction to the gate circuit model and then take a pause. I've been talking about superposition, and you have to understand how this superposition happens. The superposition is easy to visualize on a sphere. Normally, we mark the north pole as the 0 bit and the south pole as the 1 bit. And what we are doing now when we say superposition is we are allowing the bit, the qubit, to be anywhere on this sphere. And you can see where the power comes in, right? Because instead of having just the north pole and the south pole, now I have an infinite set of points on the surface of the sphere that I can use to store information. And to allow us to do that, we have this funky notation called the bracket notation. It is, as physicists, they have broken up a bracket into a left side, which is called a bra, and a right side that is called a ket. And they identify states by writing them as zeros or ones inside this bracket notation, right? And if you look at any point on the sphere, you could write it by this equation on the right, which is in terms of an angle theta and an angle phi, right? So if you go back and remember your geometry, if you are in a spherical coordinate system on a sphere of radius 1, you need two parameters, theta and phi, to measure, and even geography of latitude and longitude does the same thing, right? So you have two angles that allow you to measure, and there are certain points that are marked, which are sort of symmetric points, not just north and south, as well as the similar points along the x-axis and the y-axis. They're called the pole states, right? So these are the sort of things that we are attempting to build. And how do you build them becomes the question. You build them with artificial atoms. And this is sort of where the engineering starts kicking in. These artificial atoms are actually oscillators, and electrical circuits that oscillate are capacitors and inductors, right? So those of us who have done electrical engineering know that if you connect a capacitor and inductor together, the energy keeps getting transferred between the electric field that is stored in the capacitor and the magnetic field that is stored in the inductor. And that sort of is an electromagnetic oscillator. If you don't like to think of an electromagnetic oscillator, you can just think of it as a classical oscillator of a mass on a spring, and the same equations work. The one thing that is different is that we add what is called a Josephson junction. So if you look at a regular classical circuit, the it will oscillate, but the energy will die because of the losses in the wires. In the case of a superconducting circuit, the Josephson junction, which is superconducting, has no loss. And so the charges, which is the green and the red charges, can be moved across the Josephson junction. And as they move across that little junction, there is an electromagnetic field that is generated while the charges are moving. And then when they stop moving and they start moving in the opposite direction, then the field is generated in the opposite direction. So this little idea, this very simple idea, is what we actually implement as a qubit. Right? And these oscillators, they all have these wave functions. I remember I started my talks very early on by talking about waves. And so there is a function that describes it, and it's usually a sine or a cosine. And you can see it pictorially drawn out here. But actually, it's not just this. There are a whole series of them. We don't really use all of them. We just use the bottom two, 0 and 1, and we address those two, right? And that is how we actually work with these superconducting qubits. So if you take these superconducting qubits, zeros and ones, which are physically modeled in terms of an LC circuit, the cross out here, the purple cross, represents that Josephson junction. That is the physical model, and the physical layout is shown on the right. And you can see a little bright spot, two large green pads, which are the pads that I showed you earlier, in the little bright pink spot in the middle. That is the Josephson junction. And that is what it would actually look like, right? And then when you want to operate on it, you apply fields and you rotate the position on the sphere. So you're taking something that is on the North Pole and something that is on the South Pole, and you're ending up with something that is at 45 degrees, right? So you can do computation by looking at superposition states. And a typical computation would be something like this, which is you start on the North Pole, you apply what is known as an H gate that rotates the bit from the North Pole to the equatorial state, and then it rotates it about the z-axis so that it goes to the minus x direction, and then you rotate it again about the y-axis so that it goes to the 1 state. So these are 4 operations that are applied on a single qubit. So if you want to wrap your head around something like this, you have to think of NAND gates and XOR gates in the classical world, and say you have a bit and you're conducting some operations. In the quantum computing world, we are conducting these operations by rotating these arrows on a unit sphere. At the end of all these rotations, you have to make a measurement. And that measurement is a probabilistic measurement. So the probability of making a measurement 0 when the bit is on the equator is half, because it could be either up or down equally. So if the bit, after all these rotations, is sitting on the equatorial plane, the measurement that you make is going to give you half the probability of 0 and half the probability of 1. So this is an important idea, that quantum computation is probabilistic. It is not exact. 2 plus 2 is probably 4. It might give you 3.9, it might give you 4.1, but if you run it enough times, it will give you 4 with the maximum probability. So something like that, that's a very poor way of describing it, but some idea like that, that computation on a quantum computer is probabilistic, is important to understand. And then you build circuits. So it's not just one qubit, you can build a whole bunch of them, and you use microwave oscillators and you string them all together, and you combine LC circuits with the nonlinear oscillators and microwave strip lines. So these are topics that as students we just ran away from, and then 20 years later I find myself explaining them again. And then you take all these circuits together and you string them together, and this is an example of IBM's 53 qubit machine and the 15 qubit machines. And you'll see out here that unlike what we would call an all-to-all connection, these qubits are ordered. So 0, 1, 2, 3 is in one row, and then 0 is not connected to 13, right? 0 is connected to 1 and 14. So if I wanted 0 and 13 to interact, I actually have to go through 1 and go through 14, which under normal circumstances would have been fine, except that these are noisy. So now the more number of qubits I have to keep hopping through to make an interaction, the noisier my output goes. So 2 plus 2 may actually turn out to be 3.8, which is not very healthy, right? And that is some of the problems that we struggle with. So finally, if you start looking at all of these things put together, there's a lot of engineering that we do. So you start with, look at the bottom out here is 10 millikelvin, and then you have another stage of cooling that takes it to 55 millikelvin. And then you have something that, oh, I think those numbers are, yeah, so 0.7 Kelvin, which is 700 millikelvin. And then you go to 4 Kelvin and then 55 Kelvin. So you're basically going all the way up to room temperature or, close to room temperature through different stages of cooling. What this means is that there's an opportunity, because A, we have to understand the cooling technology. We have to understand what electronics can work at such low temperatures. How do you do custom microwave wiring at such low temperatures? How can you build amplifiers that work at such low temperatures? What is the shielding requirements and all of that? And this is all an engineering challenge. So most of my time is spent between science and an engineering, because without the engineering, the science does not work. And I think that is something that should be a takeaway message, is that a lot of the quantum computing or the quantum technology requires precision engineering. It is the precision engineering, the nano engineering, that has allowed us to get to the point where we can dream of building quantum computers. Okay, so let me pause here, take a break, and maybe have some question and answers.
Hello. Yeah, nice talk, Anil. Nice and engaging. So we have a few questions from the audience. Okay, question number 1 is, what is quantum image representation? Have you thought about that?
I am not sure what the references to. There is an area of research called quantum imaging, where we look at images, but instead of using classical light, we use single photons or entangled photons. And that sometimes gives us better imaging capabilities than what we would do with the classical light. Again, that is a signal to noise problem. So there are cases where I want to see something, but I don't want to shine any light on it in order to see it. And, I'll give a very practical example is biological samples. They tend to fade if the light is very sharp. And if you're trying to observe it and it fades, then you don't really get enough contrast. So you use entangled photons out there to do the imaging. So that is possibly what is he's referring to as quantum imaging, but I'm not entirely sure. And it's interesting. He says, please put light on it, because we put photons on it. Yeah. I can see some other questions. How accurate is the measurement technology currently? The measurement technology is probabilistic. It gets better each time. It requires a lot of cooling, and it requires very good electronics. So, for example, there are what are called superconducting nanowire detectors, and they operate also at few Kelvin temperatures, and they can detect a photon with more than 99% probability. Again, expensive. Each SNSPD nanowire, superconducting nanowire single photon detector would cost you about 1 crore for 8 channels, and a typical photon quantum computer might require 128 channels or something like that. So it's a fairly expensive thing. There are less expensive alternatives, but they're not as efficient. So depending on where your final goal is, you could be looking at large investments or not. But the technology is fairly good. I mean, if you pay the money, you'll get very good technology. is the oscillation frequency similar to what the atoms vibrate or move? Absolutely. That is why we call them artificial atoms. In fact, in one of the slides, I was showing you with the diamonds. They're called nano diamonds, and they work with particular carbon atoms or vacancies of carbon atoms, and their oscillation frequency is determined by the structure of diamond. It's a very interesting thing. I was mentioning to somebody the other day that there's a big market for diamonds, obviously, and things like a pink diamond, which might fetch more money, is actually a defect. It's a phosphorus defect in a diamond that gives it that particular color of pink. So that itself is another important spin-off technology, that as you're building these quantum computers and quantum memories, if you are able to functionalize something like that, then the jewelers of the world would love to be able to have machines that can tell the customer the quality of their purchases in real time. So that is again an opportunity for people who are looking at translating some of these technologies. What is the current position of India in quantum computing field? That is, I don't know. It's I would like to say we are number in the top 10. I don't know. Let me give a more graded answer to this. See, we do not have our own hardware today. We are trying to build it. We are trying to license it and set it up. There are many efforts going on. But while we don't have that available, there is hardware available on the cloud. So if you ask, can somebody in industry today use the quantum computers that are available on the cloud, just like any other high performance computing that is available through AWS, for example, or Google Cloud? You could just go in and access a quantum computer, right? And that means that it's a level playing field. You could go in and get access to the latest quantum computer, write the latest algorithm, solve NP-hard problem before anybody else could do it. In that sense, I know that we have a lot of manpower that is trained in software, and we could be leaders out there. On the hardware side, not so much. On the hardware side, the investments are large, and we don't, although we have been talking about trying to put together our own hardware, we still haven't done that. So the position of India in quantum computing depends on the detailed question that you're asking. On a software and algorithm and theory side, we are doing quite well. On a hardware side, perhaps not so well.
Now, 3 more questions have come up. How quantum technology can help identify inferences due to electromagnetic waves and radio frequency waves?
I'm not down
yeah,
there.
I'm not sure about this. Now, an easier question: which agency is funding universities under this mission?
Okay. The agencies today are mostly one of the ministries from the government. It could be the Department of Science and Technology that is going to be funding it. We don't have answers as yet, but it appears that it might be the Department of Science and Technology. I've got a lot of my funding from the Ministry of Electronics and Information Technology. Then my colleagues have got funded through this Department of Space. So I think each of the departments depending on their particular interest, is funding research on that.
And then Professor Prabhakar has asked a question: would quantum computers ever be able to do mathematical calculations like classical computers?
I would trust Professor Prabhakar to ask me a difficult question. So I would not do the same computations. I would do computations like classical computers in the sense that I would send a problem to a quantum computer and get an answer back. Absolutely, that is going to happen, and we are all building tools to make that happen. And they're already available. But anyone who knows Python can today, access a quantum computer. The issue is we should not take the same classical problem and put it on a quantum computer. That would be a mistake. We have to understand what the quantum computer is good for and use it where the classical computers are failing. And that is where this hybrid approach comes in. So even when you have an algorithm, there could be parts of it that work better on a classical computer and other parts that work better on a quantum computer. And that is, I think, the correct way to think about that.
Okay, and there's a question, how can a BSc physics student have practical knowledge of quantum science and technology?
There is a lot of information available online. There are free lectures available. The NPTEL, the National Program for Technology Enhanced Learning is, I know my colleagues give a lot of that, those lectures. That's a very good starting point. My own journey was like that during the pandemic. When I found that I was sitting at home, I began listening to all these lectures and understanding how quantum computers are going to get built. So I think there is a lot of opportunity out there for anybody who's interested to just go in and find the information. And if you need be, I can sort of post a link later for something like this. But if you search for quantum computing in NPTEL, you'll find the lectures out there.
And in the introduction, it was said that you have started two startups, quantum startups. Can you tell us a bit about your experiences in those?
So quantum communications was QNU Labs, and that was started pre-pandemic. So maybe I forget now, 2017 or 2018, something like that. Of course, it's been difficult as with any startup journey, but there has been enough interest that QNU has done fairly well. It has got a large order from the defense for setting up quantum links. The commercial angles are still unclear. There is better opportunity in Europe and America for commercial deployments from financial institutions. But from strategic purposes, I think, I mean, our country and all of the countries are actually investing in these things, and QNU Labs is doing quite well in that. Confluence is more recent. It's picked up a challenge of photonic quantum computing, and its competitors are actually well funded. So one has to look at what the possibilities are out there and see where the revenue models come from. I don't have very much of an idea today on Confluence because we've started it only, less than a year ago. But the journeys have been exciting. I mean, imagine you're at the forefront and you're playing with things. And I remember with QNU Labs, I always tell the story that my students would go and work there, and he would call me up and say it is not working. And I would ask him, why is it not working? He's like, I'm shaking the optical fiber. Well, I said, stop shaking the optical fiber, then it'll start working. Well, it turned out I was just being cavalier. What was happening actually was every time the Bangalore metro ran past the office, there were enough vibrations that it was affecting the measurements, right? So these are learnings that you get. I had not anticipated that it would be so sensitive, but it was clearly sensitive enough that if the metro rail was passing by, it would affect our, what is known as a quantum bit error rate, right? So I think, being on the forefront of technology and trying to build solutions with massive impact is actually something that's very exciting.
Sure. There are a lot of questions. Probably we can take towards the end and we continue with the presentation now.
Sure, we could do that. If I just noticed that these questions keep increasing.
I know. Yeah. It's very interesting to go. Yeah.
Okay. So let me continue with the presentation because I still have to tell you the other half of the story. But I am not able to close this. Okay, sorry, maybe stop sharing, then close it. All right. Okay. So since somebody asked me this question, how do you start? I just want to show you very quickly that it is not complicated. It's just some amount of linear algebra. So a circuit like this, which looks complicated, is very easy to think of in terms of linear algebra. And if you understand your linear algebra, in fact, I would recommend that you go and find a book called Quantum Computing with Linear Algebra. and it's available as a PDF. And if you read it, you'll understand that if you understand vectors and matrices, then you can do a lot of the operators, and a lot of it is just linear algebra that is working, and that's how the simulators, quantum simulators, also work, right? Okay. So the second half was this difference between gate circuit models and annealing. And this is another very interesting thing that I learned, what is almost quantum inspired. Although D-Wave is a quantum computer, it turns out that you can do annealing with anything that has waves. So I do annealing with photonics regularly now. You can also build a digital annealer very easily on a GPU-based server. So the main idea out here is something called an Ising model. An Ising model has come to us from magnetism, where you have different magnets that are pointing either all upwards or upwards and downwards and so on. And if it is a ferromagnet, then all the magnets want to point upwards. So you'll see that the left picture has the highest energy, and the lowest energy is where they are alternating up and down and up and down and so on, right? So depending on whether it's ferromagnetic or anti-ferromagnetic, you can get different configurations. The lowest energy being up and down means that this is an example of an anti-ferromagnet, right? Now, when you start a system like this, the question is, how do you get to the lowest energy state? And you can do that systematically by saying, I'll check each of these magnets and see whether its neighbors are up or down. And then if it should be in the opposite direction, I'll flip it. But if they're connected in the way it is shown out here, then you end up with some constraints. You may not actually be able to solve it easily. And that is where this idea of annealing comes in, right? I came across this paper called The Ising Formulations of Many NP Problems. Now, remember, we are solving NP hard problems, NP complete problems. This is crazy. These are problems that cannot be solved on classical computers. What are the examples of some of these problems? I will give you the examples in a bit, but you can cast 21 NP complete problems into an Ising model and solve this Ising model on an annealer, right? That is the idea. So here's one that one of my students was trying to look at, which is, let us say I have a single smart meter that I put at the input to my building. And I can only measure the voltage and current that is at the smart meter. And within the building, there are a whole bunch of lights, fans, air conditioners, water heaters being turned on and off at different times. Can I just look at the voltage and current that is entering the building and decide what are the different appliances that are inside there? So the disaggregated power could be broken into kitchen outlets, microwaves, electronics, washer dryers. And that's what the picture on the right shows you, right? And this is a hard problem which people are tackling with machine learning. You can also use quantum machine learning and do a slightly better job. And that is sort of one of the ideas. These are NP hard problems that could be solved with quantum machine learning. Different types of examples. On the left is the mathematician's version. We call it a traveling salesman problem. We call it the bin packing problem, max cut, number partition. On the right side are the applications, and that's route optimization. So how does Zomato driver figure out what route to take? Risk and minimization, portfolio optimization straight out of finance. Track reconstruction is actually something that we picked up out of the Large Hadron Collider in CERN, where they have so many detectors. They have thousands of detectors, and they need to figure out which quark was being generated. Cancer pathways. This is a crazy problem. I mean, I've had to learn biology, to understand some of this stuff. How does a cell become cancerous? What are the pathways that it takes? And if you go through all the DNA sequences and try to identify them, you may come up with pathways that cause cancer, right? And of course, decoders, which are used in classical communications all the time. So these are all NP hard problems that people try to solve. The Ising model, as I pointed out, has come from just magnetism. It's either ferromagnetic or anti-ferromagnetic. And you have to decide whether it is going to be spin up or spin down. And that has mathematically been sort of solved using techniques in statistical physics. Now, when the physicists used to solve it, they were always thinking of materials. And the materials were reasonably uniform. They were either ferromagnetic or antiferromagnetic or ferrimagnetic or something like that. Now, and they could use, sort of mean field theories where you take aggregate sort of properties. When we start talking of these kind of NP-hard problems, it doesn't become so easy to solve using pen and paper, right? Instead, you actually have to do the computation because, the traffic conditions will change when you're trying to do the route optimization. So that kind of problem is best solved now on an Ising machine, right? And this little picture shows you what it means when we're doing annealing. So you can see this little red dot is trying to find the minimum energy state. What quantum annealing allows you to do is tunnel through the barrier. So that little red dot can tunnel through and find a local minimum and then tunnel through again and find a global minimum. Whereas a classical or a simulated annealing has to jump over the barrier. So this is the idea of annealing that you can actually do with a quantum annealer. You can also do it with any other wave phenomenon, but that would be classical annealing. So in the quantum annealing case, this little Josephson junction, which is shown on the left side, the little ring out there with the Josephson junction, is connected to another loop. And the electromagnetic fields are either circulating clockwise or anti-clockwise. If they're circulating in one direction, they spin up, in the other direction, it's spin down. So each of these little spins that I had out here at the bottom is one of these loops. And then it's got some energy, and you're trying to decide what, if they're all connected together, what is the minimum energy of the system, right? So the information of your ones and zeros are encoded in this little circulating electromagnetic field, right? Or circulating current with electromagnetic field. And you have a circuit representation and you have some equations associated with it. But pictorially, again, what you're doing is you're trying to find this global minimum in this energy landscape. Now, remember that all these things are connected. So the annealer that D-Wave has is actually connected, and you can see their connectivity diagram. It has, in this particular diagram, it has eight connections. I think the newer machines has 16 connections, and there's a whole lattice of them that is connecting them all. But just like in the case of the IBM machine, everything is not connected to everything else. So I can't just solve arbitrary problems. I have to understand the problem and then put it on these computers. And that is an opportunity for us, because these are the days where, you're there are very few people who know how to do 8086 programming, and so they get paid a lot of money. Once it becomes commonplace, then everyone will know how to solve these problems, right? So there are these opportunities. You can also do things like this with light. So there are ideas of non-classical light, and this is a picture that shows you how light behaves. Normally, you have photons that come together. Then you have coherent light, which comes from a laser. And then you have single photon emitters that do anti-bunching, and they come one at a time, right? And you can use light, because remember, I showed you how light would act as a wave, and then it would act as a particle. So it would naturally have all these principles of entanglement and superposition. And you could use and build things with that. A very famous experiment which won the Nobel Prize was Hanbury, Brown, and Twiss, where they were studying stars, and they took a single photons. They looked at the light from stars and came to this conclusion that you could do what is known as a second order correlation function and decide whether it was the same star or it was different stars. Right? And we use these ideas from 1956 today, and this is where the technologies help. And so in IIT Madras itself, we have built photonic Ising machines. The photonic Ising machines can solve a lot of these problems that even D-Wave is trying to do. We do, of course, I'd say proudly, we do a better job than D-Wave itself. This particular paper, which is a 2020 paper, says how you can do it with lasers. So each laser cavity acts like a bit, and you can see how the wave function is stored inside two coupled laser cavities. It is either, in figure E, you will see that it has either got two maxima or it has got one maxima and one anti-maxima, right? And those are the two different modes that you have when you couple two cavities. And so you have a 0 bit and a 1 bit. And then people have actually coupled a whole bunch of these together and built these machines. So there are many ideas that people are coming with. So we call this quantum inspired computing, right? And we are familiar with light. We have very strong groups in photonics. And so it's very natural that we, someone in the Q&A was asking about our hardware plans. And, that's why we are pushing forward with photonic quantum computing, is because we know how to build a lot of these things, right? Okay. So the last part is the takeaway message. And I will quickly go through this. So the takeaway message is, you are looking at quantum computing, and it has different applications. You can do basic science, you can do translational research, and you can do industrial applications. But why did people get on this journey? And right at the beginning, we had discussed that cryptography was one of the main reasons that people started looking at this. They were afraid that once Shor gave us this algorithm, and we had a quantum computer, people could break our RSA encryption that we use for all our banking transactions and financial transactions. How does that work? So typically what will happen is, there is a public key and there is a secret key, and there are two parties, Alice and Bob. Alice will encrypt her information with the public key and create it, what is called a ciphertext, and then Bob will decrypt it, and then he will get plain text again. In the middle, there's an eavesdropper. And the holy grail is, how do you ensure that the eavesdropper does not get any information? Public key cryptography is of different kinds. There is RSA, which is most popular, and it is most likely insecure. There is AES, which is quite likely secure, but it is not. I mean, it depends on how many bits you're using also. RSA 2048 versus AES 256, they're all very different, right? This table out here tells you when public key cryptography will get broken. You can see that the idea is that we are looking at RSA 3072 with 128 level pre-quantum security is broken. So you would have to re-engineer these and do post-quantum cryptography, or go to larger key sizes and things like that. So the quantum computer is actually the sword. It's a spear that is going to destroy our cryptography systems. What is the shield? What is the protection? The protection is actually quantum communication, and the world paid attention when China announced its river of secrets. This is a long link from Shanghai to Beijing that will basically allow you to communicate between different government offices through the cities of Hefei, Jinan, and a lot of other cities along the way. At these major nodes of Hefei, Jinan, Beijing, and Shanghai, they have what are known as metro networks that are also protected by quantum communications. And then they have these satellite links that they did a demonstration between Beijing and I think Vienna. And that would also allow them to communicate over longer distances. So something like this is what is being built around the world today. While people are working on quantum computers, we are sure that someone will be able to crack our passwords. We are going to protect ourselves today. And so people have standards now coming out on quantum key distribution networks with trusted nodes. And then finally, the keys are shared with the cryptographic applications at a later time. So here's an example from the UK, where Cambridge has a quantum network across 3 nodes, right? And we came up with the idea that we are going to do metro area quantum access networks. It was a very catchy acronym called MACAN. So can we just build MACAN everywhere, right? In India, the status is that CDOT has been deploying these links. It's got a link running since February in Sanchar Bhavan and NIC headquarters in Delhi. It has got a link in Himachal. It has been running in academic labs. So CDOT has done some work like this. And you can see live demonstrations. If you go to Delhi, to Sanchar Bhavan, you can see how it works. There is usually a quantum channel and a classical channel that work together. And a lot of it is all engineering today. It's really not science anymore. I mean, there is some information theory and security science that we do, but a lot of it is engineering today. Our own networks are set up at IIT Madras Research Park, and SETS, which is the Society for Electronic Transaction Security, across 3 different locations. Within the research park itself, we have Bharat Electronics, we have ERNet, Anybody who's interested can get a node on that. So it's actually a growing network. Makan is a fairly successful project that has been now running. And it comes with a lot of the hardware that we have developed and a lot of the software layers for managing the network. So this is all classical work. I mean, when I tell people about quantum communications, the Q is maybe 10% of the work and the remaining 90% of it is all classical. I mean, there's nothing quantum about this FPGA board that we are using. It's all very classical, right? So the terrestrial quantum communication under the National Quantum Mission has promised that it's going to do over 2,000 kilometers, right? And I'll show you why we picked 2,000 kilometers. You have to see this picture on the bottom right, which says that, you know, point-to-point links will work to about maybe 250 or 300 kilometers without a quantum repeater. So the Chinese demonstration was using what are called secure nodes, where you're actually converting to classical and back to quantum. And we can do that today. So since we had Makan working, the next step for us was to create Kila. For those of you who don't understand Hindi, Makan is house, Kila is fort. So Kila is our next adventure to take connect Bangalore to Delhi, which is about 2,200 kilometers. And we have a test bed coming up between Chennai and Bangalore for about 350 kilometers. And along the way, we could do Hyderabad, Indore, when you go from Bangalore to Delhi, right? So something like this is an ambitious project, right? And you can imagine that no academic sitting in IIT Madras is going to be able to deploy this. And I'm hoping that there are people in this audience who are going to actually step forward and make this a reality. Chennai to Bangalore is our test bed. It turns out that it's actually not 350, it's 550 kilometers of fiber with 14 stations. And something like this is going to cost us, 60 to 80 crores, unless we can bring down the costs. And so we are now actively working on bringing down this cost, building chips, photonic integrated circuits with electronic integrated circuits. And we are hoping that by early next year, we'll have everything working, and then we can start looking at deploying something like this at a lower cost. So these are very engineering things that are happening, very translational. They're not really sitting in my lab anymore. And I strongly encourage people to reach out to any of the colleagues who are working in these areas if you find these interesting. This is actually a demonstration that was done by IIT Delhi with DRDO between Prayagraj and Vindhyachal. They were able to do 100 kilometers. So you can see the limited is about 100 kilometers. And if you need to go beyond 100 kilometers, you actually have to do secure nodes unless you get a quantum repeat. So that's sort of my time. I think it's almost up. The National Quantum Mission has 4 verticals: quantum computing, quantum communication, quantum information, or actually quantum sensing and quantum materials, not quantum information. The technologies that are working around the country are photonics, ion traps, superconducting qubits, NMR computing, spin qubits, large collaborations. It's very nice to see if you go for one of these meetings, people from across the country, hundreds of them, maybe 300 scientists sitting together and brainstorming on what is the best way of translating what they've been working on into the field, right? So reach out to your nearest universities. I'm sure there'll be someone who's interested in working with you. So I'll just end with a last slide on my Center of Excellence. We collaborate with industry, academia, and research labs. We have lots of startups now, QKrishi, Axel Quant, and of course, Confluence and QNew Labs. We have industry from Emphasis to TCS. We have academic partners, both national and international, and the research labs. So it's a growing collaboration. And I think the message is that something like this, of this magnitude, cannot be done by any single group of researchers in any single academic institution. It's going to take, as I say, the village to raise a child. So it's going to take a lot of us to pitch in for doing this. So let me stop here and use the last few minutes for questions. Thank you very much for your attention.
There are some more questions. Okay, I'm interested in theoretical aspects of quantum computing. Where do I begin?
I think the NPTEL courses, that is the same place. I think NPTEL courses cover both theory as well as applications.
NPTEL courses.
Yeah.
Sir, is any research is going on in ISRO in quantum communication for space communications?
Absolutely. They're putting up the satellite. They're working closely with PRL and Raman Research Institute and planning their quantum satellite. We are expecting that it will be up within the next few years.
Okay. I think that's about it as far as the audience questions are concerned. Let me ask you a question. Of all the qubit quantum technologies, which do you think is the most promising?
Come on. It has to be photonic because I have a startup in that.
Okay.
So I think the time scale is important. In the near term, it is superconducting qubit. But in the long term, if you talk to many people, they will tell you that photonics has to have a play. In fact, it's interesting that IBM's roadmap talks of using photonics to connect the two different QPUs. Instead of a CPU, we call it a QPU. It uses photonics to connect them. So I think that is going to be the future. There's going to be some hybridization of various things to take the best qualities out of different technology platforms.
Actually, recently there was a talk in IIT Bombay. So it was someone from IIT Pune, and he was talking about the trapped ion technology.
Yes.
What I noticed was that the processes were actually very slow. So although you may get quantum supremacy, but because the operations are so slow, so in the end, the whole thing will
correct.
Be
so that is the trade-off right now that people are struggling with. It's not very clear. So the ion traps are very good. They're very what we call the fidelity. The fidelity is very high. And that is why the quantum volume was a bad metric to compare an ion trap with a superconducting qubit. But the speed is very slow. So one has to now think about all these problems and try to find an optimal solution. It may be that there are some cases. Let us say you're trying to discover the structure of a protein. Maybe speed is not critical out there. Maybe accuracy is more critical. But if you're trying to do a route optimization, then you better do it fast. Otherwise, I mean, there's no use. Right. So I think it will become application specific.
And what is the speed of a typical operation in the superconducting qubits?
Few seconds. I mean, you can do hundreds of shots in few seconds. I think that is just see the addressing is done with microwaves, which are in gigahertz. So it's running in nanoseconds. Gigahertz means nanoseconds. So the pulses that are operating the gates and rotating the spins and everything is all happening in nanoseconds. So you can run thousands of shots within a few seconds.
Okay, there are a few more questions. Would you please suggest the university professors working in PQC implementation? I suppose the list will be very large.
Well, again, there is one NPTEL course that was run earlier this year by Dr. Shweta Agarwal from IIT Madras, and she specializes in PQC. There will be others, but this is the one I know off the top of my head.
Okay, one somewhat technical question. For photonic-based quantum technologies other than diamond, are there also the materials being investigated in India, like color centers and HBN, gallium nitride, silicon nitride?
Yes, there are. So people are looking at all of these other materials, but they don't have as much traction right now because we have a history of working with diamond. But these other materials, specifically HBN, and I think there is one carbide-based one also that silicon carbide, I think, that people are looking at.
And what is the future of cryptography in quantum computing?
So cryptography, there is a huge effort now to do post-quantum cryptography. So there are two camps. One camp that says, build quantum communication networks. Another camp that says, don't do that, that's too expensive. Redo all the cryptography to use what is called post-quantum cryptography. The danger is today there is no proof that a post-quantum cryptographic algorithm cannot be broken on a quantum computer. So there is a risk that you take if you only do post-quantum cryptography. So there too, we expect to see a hybrid approach where we set up the quantum communication links. And one of the things I failed to mention is on a quantum link, I can guarantee security only if the photon reaches the other end. But if somebody cuts the fiber or does something else, I can't guarantee any security. So at that time, you have to rely on post-quantum cryptography. So anyway, there is going to be a hybridization of PQC and QC.
Okay. So I think we have addressed all the questions, audience questions. And Abha, do you want to take over now?
Yes, sure. So thank you so much, Professor Anil. This is
Nice
really
talk.
a wonderful talk. I think covering a lot of aspects. And I think this is important in the sense that since our country is putting a lot of effort in establishing this ecosystem to develop quantum technology, and having all these details today, it's really incredible. So this is how I would like to put it up. And thank you for your time. And I really appreciate Professor Shukla to be here, despite he was not well today. And I really, not a force, but I really requested him to take up this wonderful discussion for today. So certainly we had a very good discussion in today's presentation, and means knowing about what are the verticals of this national mission, like having these quantum networks, quantum computing, and building hardware, and all these aspects are really critically important. And especially the role of, when you said about having the interdisciplinary research, means all the researchers have to come together to develop this technology is really incredible. And talking about this photonic quantum aspect, this is really new thing, and what's going on in this one when you talk about these project about the Makan and Kila. So that's really good to know about how we are actually progressing in developing a lot of aspects to have this technology taking over in the current era. So yes, so with this, I would really like to thank both of you and also the audience, and putting up a lot of interesting questions. And yeah, so on behalf of IITACB, it's a wonderful talk, and certainly audience, we would look forward to meet you again in the next talk. And thank you so much. Bye for now. Bye.
Audience
Thank you.
is very interactive today. Bye.